Hey everybody, Dr. A here, and in this video we're going to be providing some background information on pre-derived deformation formulas. So let's go ahead and get started. It turns out that we can use deformation computation procedures like the double integration method to derive formulas for theta and delta for common beam loading cases. Now, we saw this sentence in action in one of our previous videos where we derived the equation of an elastic curve, right? So what we typically do is we use pre-derived formulas to help us calculate theta or delta values much quicker, so we don't have to go through the double integration procedure over and over again. But we need to know the double integration procedure so we know how these formulas work and where they came from, okay? And so what we're going to do is we're going to look at several common beam loading cases where we have already derived equations and terminologies for theta and delta that'll make our calculations go a lot faster and more efficiently. So a couple of things to keep in mind when we do this and we use these formulas. When using these formulas, small angle theory is applicable. Now, if you recall, small angle theory says that the tangent of an angle is equal approximately to the sine of that angle of theta, and that is approximately equal to the angle itself when theta is sufficiently small. So we've seen this concept before in some of our other lectures. We typically deal with small rotations in mechanics of materials and in structural engineering in general, where we can use small angle theory, okay? We also need to note that for multiple applied loads, we can use superposition. So for example, let's say that you have a simply supported beam and you've got a uniformly distributed applied load W and you have a point load P, okay? And let's say that point load P, just for simplification cases, is equal to L over 2, all right? And so what you can do is you can rewrite this. I'm going to say equals, and I'm going to, in fact, let me move my equal sign over a little bit. I'm going to say equals, and we can rewrite this as a simply supported beam subject to W plus a simply supported beam subject just to P right in the middle at L over 2 and L over 2. So what we end up doing is we'll have a deflection for W. Let's call this, delta 1. And then we're going to have another deflection for due to the load P. Okay, we'll call this delta 2. And then, of course, in the original beam, we have this big deflection. I'm going to call it delta total. And so superposition says that delta total is just equal to delta 1 plus delta 2. So basically what superposition tells us is that if you have multiple loading scenarios on a beam, you can calculate their deflections, or a rotation angle works the same way, but their deformations separately. You can calculate a deformation due to just the uniform load in this case, and then you can add that deformation, we're calling it delta 1, to the deformation due to P alone, and you'll get the total deformation, which is what will occur when both of these loads are acting together, okay? So that brings us to a convenience factor. When you have multiple load types acting at once, you can break it down and add up their effects, all right? So what we're going to do now is we're going to take a look at some commonly loaded beam cases that we see often in real life, and we're going to see what their pre-derived formulas are looking like. So here we have a table of common simply supported beam slope and deflection formulas. So what we're looking at is a table where the leftmost column shows a graphic of a loaded beam. So for example, in that top row, we see a simply supported beam with a point load right in the middle. The second column gives us a slope angle. In this case, theta max is PL squared over 16 EI at x equals 0. That's the left support where that roller is. That's where you have the maximum rotation angle, and there's your formula there. The negative indicates a clockwise rotation, okay? And then in the the third column, you have a maximum deflection or a deflection at a particular point formula. So in this top case, you have delta max as negative PL cubed over 48 EI at x equals L over 2. So that's telling us that the maximum vertical deflection is downward. That's what the negative indicates. And it's equal to that equation. Now, the rightmost column is the equation of the elastic curve for each of these loading cases. And so this is a polynomial function that will give you the deflection at any point along the length of the beam. Now, this formula in this first case was derived for x is 0 to L over 2. It turns out that almost the same exact formula, maybe algebraically rearranged a little bit, would also be valid for L over 2 to L because you have symmetric loading, and therefore you'll have a symmetric deflection diagram. So if we kind of zoom out a little bit and scroll down, what we'll see is several other loaded beam cases with similar information. The second case shows us a point load not in the middle of the beam. The third case shows us a uniformly distributed load over the entire length of the beam. The fourth case shows us a uniformly distributed load over half of the span of that simple beam. And then the last case we have here gives us a linearly increasing load on that simple beam. Okay, so again, you've got the left column shows you the load case. The second column shows you formulas for the rotation angle. The third column gives you deflections either at a particular spot or at a maximum value. And then the rightmost column gives you the equation of the elastic curve, which is a polynomial equation. Now, we have another table that gives us common cantilever beam slope and deflection formulas. So that earlier table was showing us simple beams. This table is showing us cantilever beams. So you have a fixed connection at one end and free at the other end. And you've got the same kind of information here. You've got the second column giving you the slope angle at a particular point. The third column gives you the deflection either at a specific point or a maximum value. And then the rightmost column gives you the equation of the elastic curve, okay? So where can you find these tables, this information, besides in this video? Well, most mechanics of materials and structural analysis textbooks have tables like this in the book somewhere, okay? So depending on what kind of textbook you're using, or the author of the textbook, you'll be able to find either these exact same formulas or some other slightly different algebraic expression of these formulas. Okay, so what else can be helpful to us when we are calculating deflections? Well, another aspect is that we see when we're calculating deflections is how we handle section properties, all right? And so if you notice, all of these formulas, as well as what you saw with the double integration method, have a section property of I somewhere in them. Usually they're in the denominator of the formula, right? I is moment of inertia, okay? So where can we get moment of inertia from? So if I go back to my penultimate app, where do we get moment of inertia from? Well, again, I can be computed just like we've done in a lot of other applications, okay? Or, I'm going to say ... if we have a hot rolled steel section, we can get I from a section property table, okay? And so, again, a lot of textbooks have these, especially mechanics of materials textbooks. For example, if you use the Hibbler Mechanics of Materials textbook, this is going to be in Appendix B of the Hibbler Mech of Materials book. And so, again, what's a hot rolled section? Well, this is where steel is actually heated up, and it's shaped into a particular shape. Oftentimes we see I-shape steel sections, but they also come in C shapes, L shapes, all kinds of other types of shapes besides just an IT shape, for example. And these tables, and again, Hibbler Mech of Materials, it's Appendix B, has all of the section properties already tabulated for you, so you don't have to calculate them longhand. So I like to mention that when we say other helpful items in deformation applications, because sometimes, depending on your professor, whoever's teaching your class, they could give you a steel section that's what's called hot rolled, and you would need to go to one of these appendices and extract those section properties instead of trying to calculate the moment of inertia longhand, okay? So that concludes this background video on pre-derived deformation formulas and other helpful things involving using pre-derived formulas. Hopefully you found this useful. If you did, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.